Ele fala, não, vai ser o Thiago, não sabe o Thiago, aí ele fala, a gente está ouvindo. Pronto. Então, boa noite, pessoal. Bom, quem aqui está vendo a primeira vez na escola? Caramba, legal. Então, eu vou falar só 3 coisinhas só, porque acho que todo mundo veio para ver a aula do Sammy, mas só para comentar, né, o que é a escola de IA aqui em São Paulo. Então, nós somos uma escola gratuita, internacional, dedicada a ensinar inteligência artificial para quem quiser saber sobre isso. Então, essa é uma iniciativa, não é nossa, é uma iniciativa internacional que está acontecendo aqui em São Paulo, e aqui na Lambda, a cada 15 dias está tendo esse encontro onde a gente segue um currículo, né? Acaba que não são encontros separados. E aí, a gente deu sorte de encontrar o Sammy numa reunião que a gente teve, e ele aceitou de vir hoje. Então, geralmente a gente faz de terça, a gente abriu essa aula extra por conta da agenda dele. E aí, só para comentar, a gente também, todo o nosso conteúdo, a gente transmite online e a gente deixa gravado no nosso canal. Só no último que deu um problema, que a gente não sabe porque o vídeo sumiu. Mas, assim, vocês podem ver que é meio mega improvisado, né? Tá no meu computador, o microfone tá na webcam. Então, a gente está fazendo essa campanha no Catarse justamente para levantar fundos para a gente ter uma transmissão melhor, ter um som melhor, que as pessoas possam acompanhar, porque a gente sabe que São Paulo é grande e nem todo mundo consegue chegar no horário. Então, a gente tem... O objetivo da campanha são R$2.000, a gente chegou quase na metade. Então, quem puder contribuir, compartilhar e assim por diante, é só acessar o Catarse para... o link está na página de inscrição. Então, o último link que está lá é o link para o Catarse para a gente fazer a escola. E aí, a gente tem um mega apoio da Lambda, então a André vai apresentar rapidinho também a Lambda. E só isso que eu queria falar da escola. Isso aqui.
Boa noite. Sou funcionária da Lambda, sou voluntária na School of AI desde a primeira aula, ajudo a administrar as listas de presença e também a organizar as aulas. E hoje eu vim falar um pouquinho para vocês sobre a Lambda. A Lambda ela é uma empresa de desenvolvimento de software que entrega uma solução de ponta a ponta. E nós temos a parte de UX, UI, temos a parte de dados, inteligência artificial. E a Lambda ela abre espaço para as comunidades, né? Se vocês quiserem conhecer um pouco mais, tem aí a página, os canais. E a gente está com vagas aqui para algumas áreas, que é a área de clientes, a área de desenvolvedor de software, web e Xamarin e pessoas agilistas. Se você conhece alguém que tem esse perfil, esteja procurando uma recolocação, a gente pede que você compartilhe as vagas, que a única coisa que a Lambda pede por oferecer para nós esse local é ajuda na divulgação do nome da empresa e sobre as vagas. E estamos aqui, se vocês tiverem alguma dúvida, quiserem perguntar sobre os produtos da Lambda, a gente pode conversar depois. Obrigada.
Você vai agora trocar aqui o computador dele. E aí, a aula vai ser em inglês. Então, quem quiser perguntar em português, a gente traduz também. E aí, depois no vídeo, a gente vai adicionar captions também. Para quem não quiser acompanhar, a gente vai conseguir traduzir depois também.
Então acho que vai funcionar. Ok. Boa noite, pessoal. Obrigado por ter vindo uma sexta-feira à noite. Mas eu vou partir do Brasil amanhã muito cedo, então foi o único dia quando eu poderia fazer essa hora. é prazer de estar aqui. Então, eu espero que você vai aproveitar. Meu nome é Sammy El Ghazzal, eu sou da França, mas eu trabalho com o Google em Zurique, na Suíça. Eu trabalhei com o Google faz 4 anos e meio. Eu comecei com AdWords na propaganda por 2 anos e depois eu trabalhei com Google AI com visão computacional para reconhecer prédios, restaurantes, etc., para Google Maps. Eu fiquei 3 meses em São Paulo para trabalhar com Google Campus, para ajudar startups da residência lá. Então, eu vou falar em inglês porque eu não tive muito tempo para preparar, é um pouco mais fácil ainda de falar inglês que português. Mas se você tiver perguntas, por favor, me pergunte, pode ser em inglês, em português. Se você não puder me entender em inglês, porque eu falo demais rápido, com um sotaque um pouco francês, por favor, me avisa e não tem problemas. Eu acho que eu tentei de simplificar um pouco essa aula no máximo, mas se você tiver perguntas, por favor, pergunte, porque se você tiver a pergunta, 10 outras pessoas têm a mesma pergunta. Então é muito importante. Se fosse só para ver uma aula de SVM, você pode assistir no YouTube. Então, eu sou aqui para responder as perguntas, para tentar de ter interações e fazer uma palestra um pouco mais interessante que só sentar e assistir. Bom? Okay. So let's switch. In my brain, I need a second to switch. So today we are going to talk about support vector machines. Okay. So just to give a bit of context, if you remember in machine learning, we have 3 families of algorithms. Okay. We have supervised learning, which is you need to provide kind of the truth, right? You need to say, is this a spam email? Is this a non-spam email? You need to provide supervision, right? You have unsupervised algorithm which kind of find patterns in the data, and then you need to use these patterns in some ways to do something interesting with them, okay? And then you have reinforcement learning, which is how do you learn, how an algorithm can learn from a mistake, okay? The typical application here is like playing games, okay? So you play games, you make mistakes, and you try to maximize the score that you get, okay? So SVMs fall into this category, supervised learning, okay? And in supervised learning, you have 2 big classes of algorithm, regression and classification. Okay, so support vector machines are going to be to do classification, okay? I think you have already seen naive Bayes, if I'm correct. SVM will solve the same kind of problem as naive Bayes, okay? So now let's turn this off. Also, my handwriting is not necessarily the most beautiful thing in the world. So if you have problems reading me, you know, hopefully with speaking and reading, you should get what I say, but don't hesitate to ask me to clarify, okay? So you could ask me, why is it interesting to do support vector machines? Okay, one thing that is really good about them is they are super fast to train. In a Jupyter notebook, you can train an SVM in a couple of seconds. So it's highly interactive. We will also see that they are easy to interpret, relatively easy to interpret, to understand how the decisions are made by the algorithm. Okay, what features are important, what features are not so important, etc. Okay, so let's start with some notation to make things a bit more concrete. So I'm going to define, usually the letter small x will be a vector that has d dimension, and think of it as a feature vector. Okay, so let's take an application. We do spam classification. Okay, so my goal is you give me an email, and I have to tell you whether it's spam or non-spam. So here the features will be the words that are in the emails. Okay, so let's say for instance x can be a a vector like this, so a lot of zeros, here a 2, a lot of zeros, and here 1. So it's going to be a d-dimensional vector, maybe t is equal to 10,000. Let's say there are 10,000 different words in the English language. And here, this word will be, I don't know, there's the word cash. This word will be, there's the word earn. And this word is, I don't know, bank. And something that has nothing to do with money, school. Okay. So this vector represents an email that has once the word school, once the word bank, twice the word earn, and once the word cash. Okay, does the notation make sense to people? Yeah. Cool. Associated to this vector x, our feature vector, we will have labels, because again, we are doing supervised learning. And in SVM, typically the labels are either -1 and 1. Okay, so I'm going to start with binary classification. At the very end, I will explain you how you can use SVMs to do multi-class classification. Okay? So here we are doing binary classification, so non-spam, spam. Just because it's like the most natural, the class -1 will be non-spam, and the class 1 will be spam. Okay? Are people good with the notation? Yes. Yes, okay. It will be super important. So another example, just to give you a bit of diversity, would be imagine I'm a real estate agent, and I would like to predict, will I sell this house in the next month or not? Again, binary classification problem. This time, -1 is I will not sell in the first month, and the class 1 is the exact opposite. And here the features could be the features of the house, So let's say the first feature could be how many rooms are in the house. Then is there a swimming pool? And then the price of the house. So let's say 1 million reais, etc. Okay, let's say we have just 3 features. Okay, and again, my goal is using these features. How can I predict whether I will sell the house in the first month or not? Okay? So these are my notation. Now, how can we kind of represent this, geometrically? So I'm going to try to avoid a bit the gory math details, and I will try to focus on like geometric intuitions. I will still do a tiny bit of math just because I think it's important. If you are a bit lost in the math, don't worry about it and try to remember the intuitions. I think it's the most important. So I can only draw in 2 dimensions. So these vectors, my feature vectors, I will draw them in 2 dimensions, but you have to imagine that normally I'm talking about a vector space in d dimensions. Okay? But let's do it in 2 dimensions. So I'm going to represent my positive examples with some circles. Can people see if I write here? Yes? And I'm going to represent my negative examples in green. Okay?
Can you use, there's a black.
There's a black. Not here. Yes.
Red usually means negative, so it's a bit confusing.
Sorry? Red means negative?
Yeah, usually.
Okay. Let's do it negative. No, I mean I don't mind. And this one is positive. Okay. Now the question that SVM is trying to solve is which hyperplane, so a hyperplane is a space of dimension d-1, which hyperplane separates best these 2 sets of points. Okay? So I'm going to start with the most simple cases, which is there exists at least one hyperplane that separates the point. I will explain you a tiny bit later how do we do if we have a cross here, okay? Where in this case, no line could separate the crosses from the circles, okay? But let's start with what's called the linearly separable case. And the question is, okay, do I pick this line, or maybe something SVM like this line? And here the philosophy of SVM is you want to maximize what's called the margin, which is basically the space that you have between the closest negatives and the closest positives. Okay, you want to maximize the amount of space that you have. And this objective of maximizing the margin will decide which of the line it is. Okay? So let me just redraw here a quick example. So and here I have. Imagine I'm looking at this line. You see that the margin is going to be this distance plus this distance. Okay? But if I pick a line a bit better, this one, okay, which should be in the middle of the two sets of points, you see that now my margin is much better, is much bigger. Okay? Any question? You have a question? No. Okay. Okay, so that's the high level idea. So now let's try to formalize a bit. How does this happen? So to do this,
this line is the same concept in another algorithms like Bayes and some simple.
So naive Bayes.
So the question is this concept can be applied to other algorithms?
No, it depends. I mean, naive Bayes does not enter into this category, but for instance, logistic regression does. Logistic regression is also this idea of having a decision boundary that is a linear hyperplane. Yeah, exactly the same. Because if you do logistic regression, very quick, you will write the probability that you get a positive label given your feature vector is something like 1/1 plus exponential minus your weight vector times your features. And you see that this is going to go above 1/2 if this quantity is above, below 1. Being below 1 means this quantity is more than 0. So the separation between the probability of being of the positive class, so let me write it. Given my feature vector small x, this probability is bigger than 1/2, which is, I will pick this class if and only if W transpose X. So let me think. If W transpose X is very small, it's going to be okay. It's negative. Okay. So you see that you can write the decision boundary as W transpose X less than 0, which is the definition of a hyperplane. I will explain. I mean, let's do it now. So I have my hyperplane and I have my points. The equation of this hyperplane is W transpose X plus B is equal to 0. Okay, so just a quick reminder on this. Imagine we are in a 1D scenario. You will write the equation of a line where the two, it's a bit, okay, just be careful. Here the notation is a bit different, but I will use this notation because it's the most common. Here X and Y, they are not, Y is not the label of X. Okay? But an equation of a line will be Y is equal to 2X minus 1. Okay? And you can rewrite this as 2 minus 1 transpose vector xy minus 1 is equal to 0. Okay, so this transposing this vector times this vector, this is exactly doing the dot product between this vector and this vector. Okay? So the notation U transpose V, where U and V are two vectors, is just the dot product between vector U and vector V. Okay? Just in practice, you will often see this U transpose V rather than the dot product. It takes less time in LaTeX to type U transpose V. Okay, so the equation of the line is a weight vector, which in our case would be this, times the feature vector, which in this case is xy. But in our notation here, actually, let me try to put arrows on vectors because it will simplify a bit the understanding. So this hyperplane has an equation W transpose x plus b is equal to 0. B is just a number, okay? B equals 0 would mean the hyperplane goes to the point 0. If B is equal to something else, then it doesn't go through 0. What's the geometric interpretation of W? W is the normal to the hyperplane, okay? So let me, yeah. W is the normal to the hyperplane. So now what I would like to explain is how using this notation. Is the notation here? Do people follow the bit this hyperplane business? What? Ask a question. Don't hesitate. Really, it's like super important. I mean, if we.
It's pure math.
Huh?
Pure math.
Pure math, yeah, but it's important math. I mean, here, I'm not going to do the real math of SVM. It gets way more messy than this. But just getting this geometric interpretation, I think, is kind of important. Okay, so now what we'd like to do is compute what is the margin between these two sets of points. Okay? How do we compute the margin? To compute the margin, we need to compute if I have a point here that is represented by the vector small x. How do I compute the distance of x to this plane? Okay? To do this, I need to define here a point small x subscript 0, which is basically the orthogonal projection of x on this hyperplane. Okay? And then the distance of x to the hyperplane, let's call it capital H, is equal to the dot product between x minus x0 and the vector w that is normalized. Okay? So let absolute value because I want a distance is always positive. So let me try to explain the intuition here. X minus x0, because I define x0 as the projection of x on the hyperplane, x minus x0 and w, they are collinear, right? They are on the same line. So when I take the dot product between x minus x0 and the unit vector of w, I will get exactly the length of this vector, x minus x0. Are people good? Okay. If you want, this is exactly the length of x minus x0. So let me put arrows.
Can you repeat the length?
The length, the size of the vector.
Another question is this notation.
This is dot product. Inner product. Dot product or inner product.
Produto vetorial.
Sorry?
Produto vetorial.
I don't know. There's also the cross product, which is a different thing. I wonder if this is not the cross product.
No, I believe it's not.
Basically, I mean, if you have two vector u and v, okay? Yeah, exactly. It's the scalar product. Yeah. The dot product between u and v is the length of u times the length of v times the cosine of this angle. Okay? So inner product is basically the cosine of the two vectors times their length. Okay?
Can this be coupled with the previous distance?
Sorry?
Can this distance be calculated with Euclidean distance?
Yeah, it's the Euclidean distance.
Because it can be more dimensions, more than one dimensions at Euclidean distance. Okay.
No, the Euclidean distance works in any dimension.
And dimension, yes.
In any dimension. No problem. Yes.
It's the same if you use one or another.
This, when I don't specify anything, this means the normal distance that you're always thinking about. Okay. Not the L1 or L0, just the normal Euclidean distance.
Okay.
Yeah.
Would it work if we change the distance? Would it work or break?
Too complicated? No.
Okay.
No. Basically, no. Okay, are people clear on the notation? Don't hesitate, these are super good questions and it's important to understand the basics before we do something more complicated. Okay, so now let's look at this quantity. This quantity is basically 1 over norm of W times the absolute value. And then I'm just going to expand this, which is W scalar product X minus W scalar product X0. Okay? And I told you that this line is W scalar product X. Okay. W transpose X is just the scalar product between W and X. But now X0 is on this hyperplane. So X0 will satisfy this equation. Okay? So because X0 is on the hyperplane, it means that W scalar product X0 plus B is equal to 0. Okay? So I'm going to replace this by minus B. Let's do it. Here, this is minus B. I need to use another color because. So now what do I get? I get that the distance of my point X to the hyperplane is just Wx plus B divided by the norm of W. Okay? Again, if you don't follow all the math, don't worry, we will reconnect in a tiny bit. Now by convention, okay, because you see that if you look at this equation, the parameters that I want to learn with SVMs, they are the vector W and the scalar B. These are D plus 1 numbers that I want to learn. Okay, the x's will be my emails, and I will have, you know, the labels y, which is plus 1 or minus 1. Now you see that if I multiply W and B by 2 or 3 or 4 or whatever, it's not going to change the fact, the hyperplane. I have 1 degree of freedom, the scaling of W and B. Do people see that? If I have 2W, if I have Wx plus B equals 0, if I go 2Wx plus 2B, it's also equal to 0. Okay? So here I can choose the scaling of W and B. But instead of saying, for instance, W is of norm 1, of length 1, I'm going to say that for the points that are the closest to my boundary, so the closest positive and the closest negative, this quantity will be equal to 1. Okay? So by convention, I will not write it, but the closest positive example is going to have W transpose or scalar product of W and X plus B is equal to 1. And the closest negative example is going to have W X plus B is equal to minus 1. Okay, again, I can do this because I can scale W and B however I want. By convention, I will use this. What does it mean now? It means that my margin, okay, and this is where we will reconnect everything. It means that my margin, which is equal to the distance from the closest positive to the hyperplane plus the distance from the closest negative to the hyperplane, right? My margin is going to be 1 over norm of W for the closest positive, this quantity, which is again 1 over W because of this choice that I made here, plus this, which will be also 1 over norm of W. Okay, so the margin is 2 divided by the norm of W. Okay? I did all of this to kind of tell you how the problem of SVM, we can go from a geometric intuition to a mathematical, formula. Now our goal is the following. So I'm going to erase this and this actually. Now I told you that the philosophy of SVM is that I want to maximize this margin between the closest positive and the closest negative. Okay? So SVM wants to maximize 2 divided by norm of W. But it's a maximization with constraints. Why do I have constraints? Because if you remember, I told you by convention, the closest positive example will have this, and the closest negative will have this. So it means that for all my other data points that are not the closest to the boundary, the margin here needs to be bigger than 1. Okay? The way you write this is for all my data points. So let's say I have n data points. So for all the indices, I will have W transpose xi
Aqui basicamente é vetor. Cálculo de vetores, quando ele fala sobre
plus b multiplied by yi is bigger than 1. What is this saying? Let's say I have 1,000 data points in my data set. What I'm saying here is for each point in my data set, I will impose that this margin is bigger than 1. Because again, I made the choice that the closest points to the hyperplane are exactly at the margin of 1. Okay? So this is just saying if yi is equal to plus 1, which is the positive examples, then this quantity is bigger than 1. If you are the negative examples, this quantity needs to be less than minus 1. Okay? This is just a summary of this. Yes?
Is this really going to be achieved, or is it just a target? It's your goal to be at least 1?
No, this is called an optimization under constraint. That is, if I didn't have this constraint, and I just have this, then I can maximize easily. I just try to have a vector W that is as big as I want. It will do nothing. It will not classify anything. These constraints are what are encoding the philosophy of SVM. They are super important, and they will completely change which vector W you get as a result. But yes, they are important, and I said we are starting with a case where there exists at least one line that separates positives from negatives. So this problem is called feasible. I can find a vector W and B that satisfy all of this. The maximization here is over the vector W and B. The unknowns, the things that I want to learn, they are W and B. Okay? Now, it turns out that maximizing this quantity, 1 over W basically, is equivalent to minimizing norm of W and with the same constraints, okay? So I will not rewrite, but let me rewrite. Yi W xi plus B. Okay. Right, because maximizing 1 over W is the same as minimizing W. Okay? Exactly using the same idea is the same as minimizing the square of W, because the norm is positive, so minimizing x or minimizing x squared is the same thing. And just adding a 1/2 doesn't change anything. So if you read the book, this people will tell you the SVM algorithm is this. Okay? When you look at this, it's not clear where it came from. But if you remember, this objective, what we have here, is saying maximize my margin between the positive and the negative. Okay? And what these constraints are saying is I decided that my closest negative will have, and my closest positive will be at a distance of exactly 1. Okay? At a margin of exactly 1. So this is saying maximize the margin and all my points should be at least at a margin of 1. People good with all this? Okay, this was the most stratospheric part of the talk. We are coming back to things a bit more down to earth. Yes?
You said that we need to maximize the B.
No, the maximization happens over W and B. This notation.
W is okay, but B, because it is the right.
This notation is just saying my unknowns are W and B. I cannot just put W here because what is B then?
Okay.
It's just to say my unknowns are W and B.
No, because in B in my mind it's just the position of the line.
Yeah, but this is important. It is important.
Okay.
W just sets the direction. Imagine in 2D, W is just the slope of the line. But, okay, imagine this is my data set. And these two lines have the same slope, but the B is important to maximize the margin.
Okay.
Right?
It's
Because I want the margin to be at least 1 here and at least 1 here.
yes.
Right? So B is just the offset of my hyperplane. But I agree with you, it's a bit confusing here. You think, but in the main objective, there's no B.
So the maximization is W and B.
It's just the notation together. Exactly.
Yeah.
So it's important to see the difference about the nearest neighborhood for all of the points. You will see the distance of all the points with the hyperplane or only the nearest neighborhoods.
Sorry, I didn't understand.
The 2 points near.
Yeah, so let's say this point is the closest negative, and this point is the closest positive. Yeah. Then what?
And the distance of the
All I'm saying is this one should be at the distance of at least 1. This is what the constraint is encoding.
Okay.
Which distance exactly, I don't care. As long as it is at least 1, I'm good. Yeah. Any other question? As I said, if you have the question, 10 other people have the question. Yeah. Good?
No questions.
No? Okay.
In that case, B is a bias or is it
Again,
not?
imagine you have the hyperplane. The hyperplane has a direction, but then you can move it parallelly. Think about this. W is just the direction of the line, and B is just saying, where is my line? Yeah. So maybe let's say this is B is equal to 3, and this is b equal to 5.
So it's never possible to have a value between 1 and -1, right? So a fraction of 0 dot something.
For what?
For the closest points.
No.
Never have
No. So
less than 1 and more than
exactly. By convention, this will be 1 and this will be 1. Yeah. We are going to see how we can generalize to cases where this will be less than 1, and I will explain this. Okay, so this is the formulation. This is when the math gets a bit gory because it's an optimization problem with constraints. The way you solve this for people who know a bit of math is basically using Lagrange multipliers. This is not important. I'm just going to give you the solution.
That 1/2 is this convention, right?
Sorry?
That 1/2.
1/2, yeah.
This convention.
I put the 1/2 just to, because if you open a book at the SVM page, this will be what you see.
Okay.
Just, there's this 1/2 because when you take the derivative of this, there's a 2 that appears. It's the only reason.
Make it more tougher to find them.
No, it's exactly the same problem. It is just for people who write books.
Okay.
If you input in a program minimization without this 1/2, it will do exactly the same thing.
It's cooler.
Yeah, exactly. Just if you, I put it because if you open a book, this is what you see.
It's to be on the same page.
Exactly. Okay, the solution of this is the vector W. I will write it W star because it's the optimal point. Okay, which is my solution? Is a sum. So this is a sum sign. I have n. So n is the number of data points that I have in my training set. Okay. This I will say a word in a second. Times yi times xi. Okay. When you solve this optimization on the constraint, the way you do it is by introducing some extra variables, which are called alphas. They are called Lagrange multipliers. It's not important. Just this is a scalar, right? This is just a number. The yi's, if you remember, they are +1 or -1, and the xi, they are the feature vectors. Okay. Now, what I would like to explain is why is this important? Okay. If you remember, we go back to our okay, so the line that is the solution is roughly this line. And basically, if you look at this equation, what you are saying is that the direction of my hyperplane, W, is determined by a linear combination of my original data points. Okay? It turns out, for a lot of data points, so for a lot of indices small I, this variable alpha is equal to 0. Okay? And for only a few data points, this alpha is something that is strictly positive. Okay? Why is this important? Because if alpha I is strictly positive, then we will say that xi is called a support vector. Okay, the name support vector machines come from the fact that only a few of my original data points will determine the direction of my hyperplane. Okay? Which, geometrically, which are these support vectors? They are the points that are exactly at a distance of 1. Okay? So, this point is at a distance of 1, this one is at a distance of 1, this one at a distance of 1. This one is at a distance of, let's say, 3. This one will have alpha I equals 0. What I'm saying, basically, is that philosophically, if you were to remove that point from the training set, the line would not move. Because this point is too far from the boundary. And the philosophy of SVM is only the points that are, close to my limit between the positive and negative matter. Okay? Only this point that I circled in green are support vectors. Why are they called support vectors? Because they support my boundary. Okay? So only these points that are the closest determine my boundary. I could, again, in my head, I could remove all these points and get the same solution. Okay? Any questions so far?
So, just to repeat, this line is like the boundary, or is like the still the hyperplane?
This line is the hyperplane, right, but it is the boundary. Why? Because imagine now I get a new, you give me a new email that I have never seen, and I have to tell you whether it's spam or non-spam. Let's say the email lands here. What is my prediction? It's what was red? Red was my negative. So I will say it is spam. If it lands here, what will I say? Spam. And if it lands here, non-spam. Okay? So let's formalize actually this. Now I have done my optimization. Okay. There's one thing I have not told you, but it's not super important. I told you what is the formula for the optimal W, the optimal weight. But you could ask me, how about the optimal value for B? The optimal value for B is chosen just so that this line is exactly in the middle between the closest positive and the closest negative. Okay, so that's it. So, now how do I make predictions? So making predictions, the way I'm going to make predictions is the following. You give me a new vector that I will call X test, a test vector that I have never seen before. How do I classify this email or this house as, so let's say the email as spam or non-spam, or this house as, I will sell it in the next month or not. What I'm going to do is I'm just going to use my vector W star, which I got from the optimization, scalar product X test plus B, and I will ask, is this bigger than 0? If this is bigger than 0, I will predict +1, and if this is smaller than 0, I will predict -1. Okay? Before someone asks me if it's exactly 0, doesn't matter, just flip a coin and predict whatever. It will never happen in practice, but just in case. Okay? What this equation is saying is exactly what I told you here. Okay? If W X plus B is positive, then I predict +1. So in this example, actually, W should be this. So this side is W transpose X plus B bigger than 0, and this side is less or equal to 0. Okay? So making predictions is just asking, are you falling on this side or are you falling on this side of the hyperplane? Any questions on this? Yes?
As you told us, the closest point will determine the hyperplane. So historically, when I want to retrain my model or something, can I just throw away the extreme, the vectors that are very far from my hyperplane? It's a good practice to do that.
No, it's not. It turns out it could change a tiny bit the result, but it's not important. Basically, it's just I'm trying to give you an intuition, and what I'm telling you is the intuition is only the examples that are hard to distinguish will matter to decide the boundary. That's it. You will not, don't worry about throwing points away and all this. The algorithm will do it for you. Training an SVM on a few tens of thousands of examples is a matter of 1 second. So it's cheaper. Do not worry about, oh, I need to throw away. There's no efficiency consideration here. Okay? Yes?
Just to know, which one is the solver that you use to solve, often used to get to?
I'm not going to talk about this because it's, again, you have to write the problem as a Lagrangian, then you have to move to the dual, then you use just a quadratic solver, a basic one, and that's it. It's just, when you write all the math, you just end up with a quadratic equation on the dual variables, and then quadratic solver will do it. Any other question? Okay, so okay. Just before we're going to take a small break, so that we can breathe a bit. And I told you at the very beginning that SVMs, they are kind of interesting because they are easy to interpret. Okay, but let's come back to the example of the house that I mentioned before. And let's say I have a house. Let's say my vector X test, my new house that I want to predict, whether it will be sold in the next month or not, has 2 rooms, a swimming pool, and is sold for 1 million reais. Okay? And so this is my test vector, and my vector W star, sorry, this should be V star, is equal to, let's say 10,005. A swimming pool is, and then -1. Okay, and let's say B star is equal to 0, just to simplify. Okay, so let's say I do my training, and what my Jupyter notebooks tells me is my optimal vector W is this one. My optimal vector B, scalar B is this one. How can I interpret this weight vector? Basically, if you look at this, you are saying, so here number of rooms plus swimming pool times 10,004 minus price, and you ask whether it's positive or negative. So here you are saying if so let's 100,000 reais for each room plus 10,000 reais for a swimming pool minus the price is positive, then I will sell my house quickly. Okay, and if not, I will not sell it. Okay, so you can look at the coefficients here and understand what they mean if you understand your features. What am I saying? I'm saying for each room that I am adding, basically if the price, the price that it represents is roughly 100,000 reais. Okay? So let's say if instead of having 2 rooms, I had 20 rooms, I would add 2 million reais. Okay? Do people understand roughly? Right? Basically to counteract here an increase in price, let's say for a swimming pool, I would need my swimming pool to be, the price of a swimming pool is roughly 10,000 reais in this model. Okay, because if I have a swimming pool, my price can increase by 10,000 reais and I will still predict something positive. Okay? If my price increased by 20,000 reais, this quantity will be negative and I will say I'm not going to sell the house quickly. Do people understand? Cool. So if I look at this example, I have 2 rooms, a swimming pool, and I sell for 1 million reais. You see that here I'm not going to sell the house quickly, right? Because this is roughly 200,000 plus 10,000 minus 1 million. This is highly negative, so I'm not going to sell the house quickly. Okay? Just the point I wanted to make is by looking at the weight vector that comes out of the optimization, you can have an intuition of what are the important features. Here you see that having a swimming pool is not super important, but the number of rooms that you have in the house, super important, right?
If in decision trees, sometimes we have one variable is strong and more strong, tough, and sometimes that variable is not that so tough. in support vector machine, every time I run the model, it change the importance of the variable.
Ah, you mean is it deterministic or not?
Because for now, room is the hostess one.
Yeah. So,
But if we run again, it can be another.
normally support vector machines are deterministic.
Wow.
You can have a tiny bit of variation if the solver that you use to be fast is approximate, is making approximation. But we are talking about small variations here. Why? Again, think geometrically. Geometrically, we are saying that our goal is to put a hyperplane that separates my points that are the closest. This does not matter on how you optimize it.
Kind of, it's a problem that.
Wait, sorry. Did you finish? Was it good?
Okay, understood.
Okay. Yes.
It's, I think because that's a problem with only one solution. There is only one hyperplane that separates that.
Yes, exactly. There's only one optimal hyperplane.
Yeah.
In this situation that I showed where I can separate my points with at least one line.
That's why the answer is that question, because it's
Yeah.
always find the same solution.
Okay, so I think before we move on, let's take a 5 minutes. Yeah, 5 minute break, okay? So I think there's some, if you want to give, some calories for your brain. Any question before we?
In order to have the hyperplan,
Yeah.
I have an X training, for example, to have the array of the vector X stats so far.
Yeah, all my xi's, x1 to xn, they are my training set.
Training set, yes.
Yeah.
So if I have my X test, in the case that the point of my X test is even closer to the closest point that I have tested.
This is what I did here.
Yeah, what happens with this point?
No problem, because if you look, my decision here is it positive or negative?
So it's just positive.
This point is at least 1. To train the algorithm, you say this margin should be at least 1.
Yeah.
But at test time, it's just, does it fall on this side of the hyperplane or this one?
So it's not going to take into consideration.
The one, this notion of margin at least 1 is just during the training. Then it's just, do you fall on which side of the hyperplane? That's it.
But when I'm going to test it, I didn't understand how I'm going to...
Test, okay, test is just the name. In machine learning, you have training time, and then you have the time when you are launching this thing.
Yeah.
This is called testing.
Yeah, I know.
Yeah, that's it.
But I didn't understand what would be the output of this closest point that is...
This one?
Yeah,
Plus
1.
Considering
Plus 1,
Yeah,
because
because
this time is equal to 0.
Okay.
Okay? And I'm just saying, are you positive, which is, are you more on this side of the plane? If you are even 0.00001, you are positive.
It was just hardest to understand the...
Yeah, no.
Okay.
No, it's a fair question. It's a totally fair question. But now you understand?
Yeah, perfect.
I know, the first time I saw this number 1, I was like, why 1? You know, it turns out if it's 1 or 17, it does not matter. But people choose 1 because it's more convenient to write. But at test time, all that matters is, are you positive or negative? Any other question on this? No? Okay. So now I have talked about the most simple case of SVM, which is there exists a line or a hyperplane in general that can separate my positive from negative. But now let's see, how can I modify my algorithm to deal with more general cases? What do I mean by more general cases? Is like, I have something like this. And here, I have a barrier of lights. Okay? You see that here, I cannot have a line that separates my positive and negative because there's this red guy here. Okay? So now, if I were to write my minimization problem, which was minimize over the vector w and b, 1/2 of norm of w squared, under the constraint that for all points in my training set, the margin of my points xi is at least 1. Okay, so if you remember, this was the problem that I wrote. I try to maximize the margin, which is minimizing this quantity, and my constraint is all points should be at least at the margin of 1. If I write this problem, and I have this data set, then my algorithm will say there's no solution. Okay? And in practice, this will always happen. You will never have a case that is, works perfectly. You don't need to do anything. Okay? So now the question comes, how are we going to solve this problem? And just looking at this, okay, the optimal line should be roughly around here, right? Kind of intuitively. What I'm going to do is I'm going to introduce what's called slack variables. Okay, so sorry, I should. So this is going to be my hyperplane. This is margin equal to 1 for the negative, and this is margin is equal to 1 for the positive examples. Okay? So ideally, all my reds should be here, all my blacks should be here. And here in the middle, I should have nothing. And here I should have, of course, no red, here no blacks. Now I have this one. To solve this problem, I'm going to add what's called a slack variable. What is a slack variable? A slack variable is something that will say, this constraint is too hard to satisfy, so I'm going to make it a bit easier to satisfy. I'm going to add here a variable that I call xi, okay, the Greek letter. And this slack will say by how much am I allowed to break this hard constraint. Okay? So do people understand? Normally my red should be at the margin more than 1, so all over here. But because it's here, I'm going to add this variable, and for this variable, I'm going to pay a penalty. Okay? So let me just write how this problem changes.
So the name is slack?
Slack. Slack variable. Slack is something that's a bit, like an elastic has some slack, it's like flexible. It's called slack because it's like, how do I transform this constraint that is too harsh, too rigid, into something that is a bit more relaxed, basically. Okay? Specifically, I'm going to say, instead of the margin being at least 1, it has to be 1 minus some slack. Okay? The slack is going to be always positive. Okay, I cannot have negative slack. If I could have negative slack, I would add here a slack of -3 or whatever. Okay? This is forbidden. For this point, I will say that the slack is equal to 0. Slack equal to 0 is just saying my point is satisfying my constraints, no problem. I don't need any help. My point is already satisfying the constraint. So the slack will be positive only for points that violate constraints. But now, okay, I made my constraint a bit more loose, but I need to pay a price for this. Okay? And the price that I'm going to pay is here in my objective. This is a constant C. This is a constant that has been chosen before. I can tell you a bit afterwards how to choose it. And I'm going to pay C times the sum of slack. Okay, so I'm saying if I have too many points that violate the constraint, I'm going to pay a penalty. Okay? Are people good? I'm going to show you how these two things trade off a bit afterwards, but do people understand how the equation has changed a bit? Yes? Okay. By the way, if you have ever used scikit-learn, I guarantee you that there's this parameter C. If you have used SVM on R or whatever programming language, if you look at the API, there will be this C parameter. Someone has chosen a value for you, but in theory, you should be able to choose this value. Okay. Are people good with this? Yes?
You define C on this direction. But if I have a negative point upwards, so I wouldn't need
if I have
negative C?
This one?
Negative one. Positive, sorry.
Here?
Yes.
Yeah, here I will define a slack for this point, which is this. Okay? The slack, for the positive points, the slacks start from here and goes in this direction. For the negative points, it starts from here and goes in this direction. The slack is always defined from what is your margin equal to 1 means. For positive, this is this line, so I need to go here. For negative, I need to go here. Wait once. Oh, just 1 second. 1 second, but now imagine I have a point here. Does this point have slack or not?
No, because it will change your margin.
So who thinks yes? Who thinks yes? Who thinks no?
The rest.
Okay. It has a slack. Why? Because if it didn't have a slack, this point would be violating the constraint. Because it's not at a margin of at least 1. So this point has some slack here. It's just that this slack is smaller than 1. Okay, here slack is maybe equal to 0.6 or something. Okay?
Would it change the margin? That is the closest one.
Okay, that's a good question. So I'm going to explain in a second. Now the notion of margin is a bit hard to define because what's the margin of this data set where I have this red guy here in the middle of black guys? Doesn't mean, right? It doesn't mean anything. So now the margin will be between points that do not have slack, positive points that do not have slack, and negative points that do not have slack. Right? Your intuition of the margin, which is the points that are normal,
By the sampler.
exactly, ignoring all these points that are a bit annoying. Yes. Yes.
There is interpretation for the slacks, like a vector or a
No,
distance.
no, the slack is just a number. The slack is just a scalar number. Yeah. And again, if you look at this it's a scalar because it's basically a distance. Is by how much am I?
So it's a distance. Okay. So
I mean, the distance is a scalar, right?
Yes, but it's always positive distance.
Yeah, I mean, I wrote it here.
Okay.
Yeah, right. It's a scalar that is non-negative.
Okay.
Yeah. Yes.
How the model will differentiate between if it is a slacked point or just normal point?
The model doesn't care. The model is just you give it this optimization problem and it will do something.
But imagine the red point is a black point.
This
How
one?
do you differentiate red point to red point? Because there.
No, wait. I know in advance here I'm at training time.
Okay.
At training time, I know if a point is black or is red.
Yes. Right.
So at training time, I know.
But when they predict how.
No. So when I'm predicting, it's exactly as before. If you fall on this side, you are positive. If you fall on this side, you are negative.
Okay.
At testing time, so
There
with
is no
new
slack.
points, no one cares what slack. Slack is just to train the algorithm.
Okay. Right.
Okay. Okay, now I would like, so this was kind of a motivation for the slack. I would like to give you an intuition of why having slack is important. So, of course, here, if you have no slack, you cannot solve the problem. It will be a bit annoying, right? But let's look at another example that hopefully will convince you of the importance. And let's say I have this very simple data set, which is the following. And here I have just one point. Okay? And let's imagine that I have lots of red points here and lots of black points here. If I do SVM, so this data set is linearly separable, right? I could find a line that separates my red and my black without any problems. Where would be the line? If I do normal SVM, it would be here.
Yes.
Right? Okay. Do people think it's a good decision to do this? No. But if I do SVM without slack, this is my decision boundary now. Okay? Just because of this one, maybe I have 1 million point here. Just because of this one guy, I start making, I put my decision boundary here. Now, if I allow for some slack, what am I going to do? I'm going to pick this line as a separation. I mean, when I say I pick, it's like the algorithm will pick. And what will it do? It will just add a bit of slack here, just for this one point. Okay, this is margin equal 1. So I need to add just for this one point. So let me write here. This is SVM without slack, and this is SVM with slack. Yeah. So I'm just going to say, instead of, because of this one outlier, this one extra point, moving my decision boundary here, let's just keep it here, and just for this one I will pay a price. But it's a price that I'm willing to pay because there's just one point that has slack, sorry. So this will be small. I'm okay, but I will have a much better decision boundary. What do I mean by much better? This decision boundary generalizes to new examples much better, right? If just because of this one example, I put the line here, this would typically be a case of overfitting. You know, I'm trying to respect too much my training set. Yeah.
We will generalize it better, but we will lose that accuracy. That's what we will.
But only at training.
Yeah. And the prediction will say it's positive.
But at training time, I don't care about predictions. At training time, all I care about is here, minimizing this objective. And by minimizing this objective, yes, for this one point, I pay this penalty C, but I have a much better margin,
Yes,
right? Here the margin is very small,
yes,
right? Here the margin is much bigger.
yes.
My goal is to maximize the margin. So to minimize, let's say, the inverse of the margin plus the penalty. Here, no penalty, but very small margin. Here, a small penalty just for this one point, but a big margin. And the algorithm will say, oh, it's better to have a big margin and just pay the penalty for this one point. It's not going to know on its own, oh, this is overfitting, I avoid overfitting. Of course, here I'm simplifying to try to explain to you a bit what's the... It turns out there's a continuum between these two lines, okay? What is this continuum? It's driven by this parameter C. Let's say if I pick C very, very big, C is equal to plus infinity. What does it mean intuitively? C is equal to plus infinity means that if I have even a tiny bit of slack, I will pay such a big penalty. Or let's not say infinity, but C is equal to 1 billion. Even if I have a tiny bit of slack, I pay a huge penalty for it. What will my algorithm do between these two lines? Huh?
I didn't understand the question.
If I have C is equal to 1 billion, which of the green or the blue line my algorithm is going to pick? Yeah, the green line. Because the blue line would have this slack, and because C is equal to 1 billion, I will pay a huge penalty, and my goal is to try to minimize this objective, right? Now, if C is very, very small, I'm going to allow for a lot of slack, maybe too much slack, okay? So, you have to find a value of C that is good, right? So, C too big means you are too rigid, C too small, you are too relaxed, okay? For people who already do machine learning, the way you pick this C is by cross-validation, okay?
So, for instance, if the new data points is closer to X, then you're gonna pick on the cross-validation.
Sorry, whoa.
So imagine that you have new points.
What is a new point? A test point?
Yeah, test points
Okay.
that is closer, but they are red, but they're closer.
No, but it's a test point. I don't know if it's red or black. Right. A test point is I have to determine to tell you whether it's red or black.
Right. But imagine that it's a test point, and you're testing, and you know that is a red one, but the point is closer to this.
Again, at test time, all that matters is which side of the plane are you on. At test time, all I care about is I have my hyperplane. Do you fall on this side or this side? That's it. At test time, forget about the slack, forget about C, forget about everything. At test time, all I have is W and B, and I tell you, is W transpose X plus B positive or not? That's it. This constancy, this slack, all of this, they are just at training time. How do you make your algorithm a bit more clever, a bit more flexible for mistakes or this type of things? Any question about this? No? Okay, what time is it? Yes?
Is there any relationship for us to pick an initial C to start playing around?
Again, C is not a variable, an unknown. C is a constant that you have to choose.
Yes, so that's my point. Should I start with 1 or 1 million?
And there's a default value inside.
Yeah, the default. I don't know how much it is. Probably it's 10 to the minus 2 or 10 to the minus 3 in scikit. Again, you have to try different values of C and see which one is the best for you. That's the short answer. There's no good recommendation for C. But C equal 1 billion is not a good value. Okay. Any other question? Because we're going to move on to like the last topic of the night. Yeah.
I'd like to understand better what do you mean about penalty?
Okay.
Sorry.
My objective is to minimize this quantity. Let's forget about everything that is red. Let's forget about the stack. My objective is to minimize this quantity. Now I said, oh, if I just have the black problem here, I cannot solve it. So I need to add something else to make the problem feasible. Okay? What I add is these slack variables. But what I'm saying is to allow for this amount of slack, to allow for having points at a margin less than 1, for violating my initial constraints. I have to pay a price. I call this a penalty because you see that if you have a slack that is very big, it becomes harder to minimize. Okay? That's why I call it a penalty.
One more question. This is not the case that I needed to take off the outlier before to...
No, but here, the algorithm will deal with the outliers. It may be that you have so many outliers or such extreme outliers that they become a problem, but normally you should not have to do the pre-processing yourself.
Because the SVM is not good to work with outlier values, right?
It should. It should, again, because it should say, oh, if you have one outlier, just for this outlier you pay some slack penalty, but I have a general line.
Okay, but best practice is stay with the outlier, try your model.
It's hard to say best practice or not best. I say in linear regression, you have an outlier, you are screwed. In SVM, normally you are not screwed. Not too much. No, but it depends how extreme your values are. I cannot tell you in advance. If you know the point is an outlier, take it, just remove it. But in general, you don't know what this will. It's more you do something and you see you have something completely messed up, and then you're like, oh, this point is an outlier. Okay. My guess is with SVM, you will not even notice that the point is an outlier. But yeah.
I think that the point is that I think no model can work well on outliers.
No, but that's not true. That's not true because here again, you can allow for outliers.
But if they are outliers on test time, it's kind of
no, but outliers at test time. No,
yes, no model is
going to work. At test time,
yes,
again here, no, but at test time, whatever happens.
Yes.
If it's an outlier, it probably means that you cannot classify it.
Yes, that's my point. So.
Okay, any more questions? So everything we have discussed so far is called a linear SVM. Why is it linear? Because this hyperplane, right, is just basically a linear hyperplane. It's just in the original vector space, A hyperplane is just a linear structure. Okay? But now, what happens if I have the following data set? Imagine I have the following data set. Okay? You see that using a line in this 2D case to separate my reds from my blacks is not going to be a good thing, right? You run SVM with Slack, it will give you a line. Okay, but the line, I don't know where it will be, maybe it's here. It's not super good at separating the red points and the black points, right? So now the question that comes is, how can I change my formulation of SVM to basically accommodate for this type of cases? Okay. So I'm going to talk about something that's called kernel method, which is how do you transform an algorithm that is linear into something that is non-linear? Okay. And I have to say, who knows what K means here? Not many people. Okay. Just when you know, the next speaker comes and talks about K-means, ask him or her, what's the kernel method for K-means? Okay. Now, kernel methods is more general than just SVM. I'm going to try to give you the intuition. The math behind kernel method is a bit involved too, but I will try to give you just an intuition of how it works. The intuition of kernel methods is we are going to change the scalar product to a new scalar product. Okay? So this will become a kernel function applied to vector u and vector v. So here, okay, you can also call this the linear kernel. Okay? We're going to move to a function k. I will tell you what the function k is doing. But the function k is taking a vector u and a vector v, and it's basically, instead of measuring the inner product between two vectors in the normal way, the natural way, we're going to change this definition of the dot product to something a bit more complicated, and that will be given by the kernel. This kernel is actually itself a dot product, but in a new space. Okay? So let me try to... We're going to see an example to make it a bit more concrete, but basically I'm saying I had the normal inner product in my vector space here, but instead of doing the inner product here, in my head, I'm going to move to a new space, and in this new space do the dot product. Okay? What does it mean? It means the way you measure angles, the way you measure distances is going to change in this new space. Okay? So let's say here I have my points, okay? They have two coordinates, x1 and x2. And let's say I'm going to move to a new space by using a transformation phi, okay, which is this phi. And phi, which takes a vector x1, x2, is simply x1 squared plus x2 squared. Okay? So I move from a 2D space to a 1D space, right? And in this 1D space, how do my points look? Okay, my points will roughly look something like this. And okay, are people good with this? So my origin is here. I should have drawn. So this is the vector 0. So basically, I moved. I take this point. It has a norm squared of, let's say, 4. It goes here. number 4. And here this is, let's say, 10. So this point is at the norm square of 4. This point is at the norm square of 3. This point is at the norm square of 4.5. All my points land roughly around 4. And here, same for the black points, roughly at the distance of 10. The numbers don't matter. My point is that with this transformation, I went from a problem where it's impossible to separate points with a line to a problem where it's now easy to separate with a line, right? Just here, I will say this is my line. Everything that is here, I classify as positive. Everything that is here, I classify as negative. Okay? So, again, the math behind kernels is kind of complicated, but just the intuition is the following. I'm going to introduce non-linearity in my decision boundary by applying a transformation to all my data points, move to a new space, and solve the normal SVM in this space. Okay? A linear SVM in this space. Okay? Just 1 second. Now this decision boundary here, this line that I have fitted here by running SVM in this space, what does it mean in this space? What does the decision boundary look like? It looks like a circle. Okay? Again, the idea is the non-linearity of my decision boundary here comes because of this transformation of my data points here. This transformation comes from the fact that I change my normal dot product to a new dot product which is given by the kernel. Okay? Are people good with the intuition? Yes?
I don't know how do you find a good...
No, okay.
Okay.
1 second. I'll come to that.
Okay.
Yes?
In your example, the distance of 10 is the nearest point of the center of the circle
No,
to
it's
the first black.
just this distance, it's roughly around 10. This point is 9.8, this point is 10.2. It's just, I need to put a value just to
Okay.
doesn't matter.
Yeah.
It's roughly this norm square is 10, this one is 11, this one. Okay. Yes?
I'm very tempted to look at this line as a z-axis and look from here to the board. Is this correct?
No.
Correct situation?
This is a new space. This space has nothing to do with this one. It's a completely new space. Yes?
I need to see some kind of visualization to choose because
No, okay. In a second. Yeah, same question. Same question. Yes?
Is there x1 squared?
Yes. Yeah. Basically what I'm saying is here my feature map, so my transformation phi is just I take the vector and I return its norm squared. Its distance to the origin, to the vector 0. Okay, so now the thing that is kind of confusing is here I showed you an example where I told you I'm going to pick this transformation phi that is this. Okay? Because we are in 2D, I can plot the data set, I can tell you. The reality is you will never choose phi yourself. Okay? So this part is a bit mind twisting. You are not going to choose phi directly. You are just going to choose phi by picking a kernel. So the degree of freedom that you have is which kernel do you want to apply. So when you are going to apply SVM and you are going to use scikit, you will see there's an argument that is called kernel, I guess, or something like this. I should have checked. I think it's called kernel. The default is linear. Kernel linear means I do normal SVM. Okay? And then you will have two other kernels, which is the Gaussian kernel or radial basis function, and the polynomial kernel. Okay, so I'm going to show you these two examples. But your degree of freedom is what function k do you pick here? The choice of k determines the choice of the transformation. But you are not controlling directly this transformation, and it does not matter. Okay? All that matters is which kernel are you picking. Okay? Let's see the two examples of kernels that are the most common.
So before you erase, like this, no, it's like this green line that is, is the vector.
Yeah.
Is the boundary line right now?
Yeah. It's, but again, I was in this space. This is the problem that I want to solve. To solve this problem, I move to this new space, solve SVM here. But what do I care about is what is this green line here, right? Because okay, this is my training set. And I told you, okay, this line here in this space is this. Why do I care only about this space? Because when you are going to give me a new point, what I want to ask is it inside the circle or outside of the circle?
So for instance, the kernel, like the linear method, not to apply right after, like to actually use to turn it into that when you choose a kernel method.
Well,
you know, for instance, you thought there's a linear, there's a polynomial, and so on. So you're going to use to turn to D1D.
No. Linear kernel is, forget about everything that I have talked in this second part, is the SVM that we talked in the first part.
Yeah. But you call that a kernel method. One of the kernel is linear.
Kernel linear just means we are doing normal SVM. The thing that we saw before is basically this function phi is the identity. You do not do any transformation. The situation, this would be exactly the same here. This is linear kernel.
All kernels that we apply can be used to plot the boundary on the other original plane.
Here
so you don't lose the exponential property of this.
Okay, good question. When you use kernels, you lose the explanation property of SVM. You know, before I told you can look at the W that you get after optimization. This is not true anymore. You cannot look at the vector W. You do not have access to it. Okay, the two examples of kernels. The first one is what's called the polynomial kernel. And between two vectors u and v. And it's simply going to be the dot product between u and v. Okay. Let's say plus 1 raised to the power of t. So the polynomial kernel is you take the normal dot product and you raise it to the power of d. Philosophically, what is this going to do? Let's say I have my vector u. Normally, my features will be u1 to ud. Okay? My vector u is a d-dimensional vector because I have d features. Basically, what this polynomial kernel is going to do is going to introduce u1 squared, u2 squared, u1 times v1, u1 times v2, etc. It's going to introduce things that are between u and v, and then also raise some of the u's to some powers. Okay? This is intuitively what it's doing. Okay? And then you have what's called the Gaussian kernel, also called radial basis function, which is the kernel between u and v is exponential minus the distance between u and v squared divided by 2. Okay, fine. So, yeah, just 1 second. So you see here, I look at this, no idea what this transformation phi is. But it does not matter again because the only thing I have control over is, do I pick polynomial, do I pick Gaussian, or do I pick linear, the normal thing? If you can, it is best to pick linear because you can interpret your decisions, etc. But if linear doesn't give you good performance, then you have to try Gaussian and polynomial. Okay? The way you make the decision between Gaussian and polynomial is you have to try. You have to try and do cross-validation. Okay? Same thing. How do you pick the degree of the polynomial here? Do you pick 1? Do you pick 17? Do you pick 2, 3? Again, cross-validation. You have to try different values and see what gives you the best generalization. Okay? Yes? Who had the question? Yes?
You said the radial basis function kernel, but it's only because of the exponential. Because
I didn't pick the name, someone else did.
I know, but
I wish I was the.
Why do you wish?
Imagine I could put my name here. You know?
No, I'm saying that because I read the resume of SVM and they said we try to use this as a simplification of radial basis function.
To use what?
You use the kernel. They say that kernel based function because of the exponential, but it's not radial based function. Okay.
The name is everyone will. I call it Gaussian kernel. In scikit it's called Gaussian kernel, but sometimes you will see radial basis function. I didn't choose. I have no control over naming. I'm just telling you in the literature, this is what you will see. But yeah, it's true that why is it called Gaussian is because this looks roughly like a Gaussian distribution. You know, if I want it to be completely, complete, I would add here a variance, which is another hyperparameter that you need to do with cross-validation. Does not matter for what we want to discuss.
Okay. I think that what it means is that RPF can be its own model. Radial basis has its own
I think yeah.
Not just kernel tree.
No. Yeah. No. So I agree that this term is overloaded, is used for other things. Yeah. Sorry, I didn't. Yeah.
This I ask it because sometimes it's changed my mind, but. What about?
Yeah, no, but unfortunately, naming is
confused. I was confused about the name.
Naming has a lot of conflicts. Some people will, even if you take the Gaussian distribution, some people will call it a normal distribution. You just have to deal with it. That's just life.
So the kernel, it's like an activation function.
No. Here, activation function, you start entering deep learning. This has nothing to do with deep learning. Yeah.
Okay, thank you.
Any other question? I mean, the only similarity with an activation, the kernel is the way to introduce the nonlinearity in the model. That's the only similarity. Any question? No? Okay, because we are going to look at a few slides just to conclude. I think, yes. What time is it? Okay, we're good. I just want to show you a few visualization of what are kernels doing. Okay. Right. So one thing I forgot to say: when you pick a kernel that is polynomial or Gaussian, the idea is that this transformation, you know, when I said we move to this space, to this new space, the idea is that this transformation is moving to, let's say, we have 100 features, and with the transformation, we are moving to something that is higher dimensional. Why higher dimensional? Because when you have more dimension, you have more space between the points to find a line or a plane that separates them. Okay? So, again, you do not control the transformation, but when you pick another kernel, philosophically, you are moving to a higher dimensional space. Okay? Here, the only thing I wanted to show you is I use a polynomial kernel, and you know I have this parameter small d, the degree of the polynomial. And I told you the way you pick this d is using cross-validation. So here I try different values of d. By the way, I say I, it's from a paper, I didn't write the paper. Again, I wish, but... So I move the degree of the polynomial, and I plot here my validation error. Okay? You see that here, I would probably pick degree equal to 2, right? Because then you are kind of overfitting. Okay? Let's forget about this for a second. Okay, degree of 1 is just I'm doing linear SVM. So originally I had 256 features. Okay, so let's say if we go to the spam examples, we have 256 words in the alphabet. Okay? When I start increasing the degree of the polynomial, the space in which I am going has a dimension that is increasing a lot. If I use a degree of 2, I'm already at 30,000 dimensions. Okay? I go degree of 3, roughly 1 million dimensions, etc. Okay, so again, the idea of the kernel is I move to a high dimensional space where it's easier to find separators in the space. Okay? Now, a few toy examples just to try to get an intuition of what does it do to apply a kernel. So this is a visualization of applying a Gaussian kernel to SVM. And here we are looking inside in the original space. What does the decision boundary look like? Okay? You see that here I'm going to predict negative. Here, same. Here, predict positive. So positive are the circles, negative are the triangles. And here also positive. So you see that the decision boundary is clearly non-linear. And the fact that we apply a Gaussian kernel, what is it creating? Imagine you are actually having Gaussian distributions here. So here you have a Gaussian distribution centered here, and with a variance that is roughly this. Here you have another Gaussian distribution, a negative one, with a variance roughly this. Same here, same here. Okay? So basically, Gaussian kernel, imagine you are in your input space putting a few Gaussians, and then you are saying, is there a lot of triangles? If so, I will say it's red. If it's a lot of circles, I will say it's blue. Okay? That's what kind of the Gaussian kernel is doing for SVM. Yes?
There is some similarity with centroids.
Yeah, I mean, centroid is a very generic word. But yeah, you could say here is the center of the distribution. And now, applying polynomial kernel. So these two examples are polynomial kernel of degree 2. So here my goal is to separate these white dots from these black dots. Okay? You see I apply a polynomial of degree 2, and this is the decision boundary that I get. Okay? I'm going to make some mistakes. Here there's a white that is misclassified, and here there are a few blacks that are misclassified. But my decision boundary overall looks kind of good. This looks like an ellipse, right? Here, this looks like what's something that's called a hyperbole. If you know a bit about quadratic function in 2D space, the two classes of quadratic functions are either ellipses or hyperboles. So that's where it comes from. But here, same. So I had a lot of white dots here, black dots here, black dots here. And using this polynomial of degree 2 for the kernel, I managed to have a decision boundary that is much more complicated than a simple line. Okay? Are people good with this? Yes. Again, the idea of kernel, I don't expect you to walk out and be like, okay, I know everything about kernel. But I think it's good to have a few intuitions on what it means. It's very subtle, you know, and we didn't do the math, but it's very subtle, I agree, I know it. I hope I managed to give you a rough intuition of what it is. And yeah, there was a last section.
So,
Yeah.
So, first one's like, are SVMs, what's the real use case that SVMs are used today, like in production systems?
Mm-hmm.
And sometimes when we teach AI classes, machine learning classes, some people say that I like to know the intuition, but we'll just try scikit-learn and see what happens.
Mm-hmm.
So, how big is important to really know the intuition and not, you know, like just trying out stuff until you get some.
Yeah. It's a matter of philosophy, I have to say. I am part of the people who think it's important to have a rough intuition of what's going on, because if you don't, when you have a problem, you have no idea what's happening.
Right.
You know, and in machine learning, you don't have tests, you don't have, you know, if you don't have some insight into what's happening, you will never debug anything. That's just my personal, you know, opinion. Some people will tell you, listen, I want to do a platform where everyone can do machine learning by just the click of a mouse. I think it's also valid. It's just not my favorite option. I think it's better to educate people, at least with very rough intuition. I'm not telling you, I didn't show you the math, how do we solve this optimization under constraints? Because I think it does not matter. But I think that next time you are going to use scikit and you will see, this parameter C, I know where this C is coming from, the amount of penalty that I'm doing. This kernel parameter that, you know, scikit tells me can be linear, polynomial. I know, I have a rough intuition into what it means. Of course, you could just be like, okay, let me try polynomial. Better, cool. But you have no idea what you are doing.
So I asked that because it's a kind of discussion that arises every time we discuss a full curriculum to the school.
I think you should have a rough intuition of the algorithms. But that's, again, just my point of view. You know, other people.
Now the teachers think it is as well.
Yeah. I think it's because it's easy to do the programmation part of the coding part of machine learning. You know, you can just change parameters and something will happen. But again, you know, if you don't know what is overfitting, if you don't know what metrics mean, if you don't know what, you know, you have accuracy but you have precision recall. If you have no idea of all this, I don't think you are going to make the right decisions for your problem. And I think at the end of the day, you have to remember that you start with problems, not with just, okay, I write something and it works and I'm happy. But, okay.
Yeah. So, what is the real production application that uses SVMs today?
So, I mean, I would say if you have not too much data, SVM are still a very, very good candidate. And if you want basically a simple algorithm that will do the job for a data set that has a few thousand points, SVM is like a good candidate. Basically, if I had to do classification with a simple algorithm, I would try SVM or logistic regression. Maybe naive Bayes for some applications. But these two, they are the easiest thing. Yeah, that's it. Yes?
While studying deep learning, I saw that sometimes only descriptive statistic is good. Descriptive statistic. Like traditional statistical. To do classification or regression. So it's like logistic regression. I don't know much about logistics, about statistics, but so I would like to know if statistician may have some different tools to apply that it's not from deep learning.
So yeah. So of course there are some.
Basically, I want to know if I should worry about statistics.
I mean, I think you should always be curious.
Not very.
I think it's good to have basic statistics education, but again, if you talk to me, I would tell you that anyone on the street should know basic statistics, because otherwise, on the news I can tell them whatever, and they do not understand, numbers and this. It's just a point of view, I don't have an answer to tell you do this or do that. Okay, so that's it, I finished with the math. It's just, I think a few of you were a bit curious about, what is the daily life of someone who works in machine learning. So I have just like 2 or 3 slides just to talk about what I do during the days, kind of. Okay, 90% of my job is not the fun part we discussed, okay? 90% of my job is getting data, getting good data, cleaning data, adding labels. This is the hard part of machine learning. Applying algorithm, as we discussed, just change something in an API and you have a result. But getting good data, all this is important. Who knows what this is?
Mechanical Turk.
Mechanical Turk. Okay. So the story behind Mechanical Turk is a bit funny. This guy who was in Holland is 17th or 18th century. He was like talking to kings and everything and saying that he had created a machine that could play chess. Yeah. The reality was there was just one guy inside the machine who was actually playing chess, but he fooled a lot of people. Why am I talking about this? Because when you want to, let's say you want to do classification of images or classification of emails between spam and non-spam. What you can do is use what's called a mechanical Turk, send your email and say to a person, an actual human, is this a spam or is it non-spam? Okay? And this platform of having kind of humans who will look at your data and annotate quickly with spam, non-spam, or there's a cat in the image, there's no cat in the image, it's called mechanical Turk. So just something related to today. But 90% of the job, data.
So the one example of that is captcha, for instance.
Is?
Captcha. When you Google an image, then you classify like street lane is yeah.
Yes.
Right.
Yes. So here you act as a mechanical Turk. You are part. It's one of the strategies that companies use to actually get some data. But there are also platforms, people who you can contract. Amazon has a platform that's called Amazon Mechanical Turk. You pay for each image or whatever example that you want to annotate, and you tell them, I'm going to send you 1 million examples. How much would I pay to get spam, non-spam annotations, or etc. Okay, my second thing that is very important is the metrics. This sounds trivial, but whether you are looking at accuracy, precision recall, L2 distance, picking metrics is actually something, a bit of an art. Okay, just to. Sorry, you have a question? I just picked 2 applications, okay, which are, imagine, here detecting pedestrians for self-driving cars or whatever, and classifying spam. Here you have 2 types of error when you classify spam. Emails that are non-spam and that you classify as spam, you are sending good emails to your spam box. And emails that are spam, but you believe they are non-spam, you leave them in your inbox. Okay? You also have 2 types of problems here, which is you think that this human is actually not a pedestrian. Okay? The other case is, you think that this tree is a human. Okay? You see that here, believing that a human is not a pedestrian will have bad consequences, okay? Versus the other type of error, or you believe that this tree is a human, okay, your car will be more careful, but it's okay. So, super important to think what is the trade-off between different metrics, different types of error. You know, at first I tell you precision recall, you will think, oh, again, this sounds trivial, but when you are dealing with real-life problems, this becomes really important. Okay? And again, here, are you happy to send some of good emails of your users to a spam box? Maybe not so much, right? So, work on metrics, I don't know, 5% of my time, maybe, I don't know. Just to give you a rough idea. And the fun part, which is experiments. You know, you have an SVM, you try polynomial kernel, Gaussian kernel, you try to change degrees. The reason why I put this meme is because it's the first meme I saw when I joined Google, and it summarized perfectly, you know, when I arrived, I was like, what am I doing here? It's actually also how I felt when I arrived in Brazil, you know? I was like, wow. So, and I have just to, okay. This is what I call old school debugging. It's not old school, people still do it, you know, setting up breakpoints in programs, trying to understand what is the value of the variable here, what is the, you know, old school debugging. This is the machine learning debugging. You have to look at examples. Oh, here, I'm classifying this tape player as a cellular phone. What's happening? Or here, this is my true distribution of labels, let's say the prices of houses. But my predictions are a bit different. Maybe the mean is similar, but the variance is completely messed up. Okay, let's try to understand here. What I'm saying is this type of debugging is a bit more, something more of an art, less deterministic, less, oh, I look at this variable and now I understand, I can follow what's happening. Here it's like, this is what you plot, now tell me what's happening. So you have to try to get intuitions, oh, okay, why am I making predictions with a variance that is so big and it should be just this small? Okay, so it's trying to understand what mistakes is your algorithm doing, what can you do to address these failures, okay? This takes also a lot of time, right? It's not, changing an algorithm is super easy, it takes like 5 seconds, but actually looking at this and being like, okay, why is this algorithm or why is this kernel better than this one is a bit more subtle. And you know, I will just finish with this small cartoon. This is written 2007, but this could be the beginning of time to 2007. You know, when programmers are chilling, reading articles or whatever, you could say, oh, but my code is compiling. Now when you do deep learning, you can say my network is training. and the time horizons are very different. Compiling a program is in the order of minutes. Training a network can take 1 day, 2 days, 3 days, right? So, of course, you are not chilling when the network is training, right? You are preparing the next thing. You are preparing the infrastructure to look at your data, to, you know, you are not waiting there to just, oh, that's. Anyway. And I will share the slides with Clayton afterwards. But I put 2 references, which is the original article on support vector machines. It was actually called Support Vector Networks from, I think, 1995. And I put a link to the notes, the class notes from the Stanford class on SVM. Here you have all the gory details of mathematics if you want to get into this. But yeah, if you want to dig down a bit more. And that's it. Yeah, sure.
So, for instance, when you're in a big company, and so you told that most of the time is getting data. So, how is actually the workflow? There are some engineers that only focus on getting data, on cleaning, and so on, or you know, you're kind of responsible for the entire workflow.
I don't have a good answer to this because it depends. It depends on projects, it depends on companies, it depends on everything. I will tell you what I think. I think it's important to be involved in all the steps. Because if you are just doing modeling, but you have no idea about what type of data you are modeling, this is not good because you have no insight, no good understanding. Sometimes the task of getting data is too big. So you need to have someone who is doing more infrastructure work, pipelines that transform the data. But I think that the person who is doing modeling also needs to look at the data. It cannot just be, oh, I write Python code to do SVMs and all, and have no clue about what is the input. Because without intuition, I don't think we can build good models. But it's my point of view, others will think differently. And you will see a lot of companies which are data engineer and data scientist. That's, yeah, different philosophy.
And the day-to-day to test and train, you usually work with Python plus Jupyter notebooks, or you?
Yeah, so we have like an internal Jupyter notebooks, which is called Colab. It's actually open source now. Not open source, but people can use it on the outside. And then yeah, Python, because TensorFlow is in Python. So to train deep neural networks, we use TensorFlow. And then the pipelines, it depends. But you know, you can have Go, you can have Java, C++, whatever.
What's your favorite code editor?
Huh? Code editor? I don't think it matters. You know, it's implementation detail.
You usually work with?
I use Vim. I'm somewhat of an old schooler myself, you know. Yeah.
And the question is about the reference. Stanford classes, I after it long ago, but I only find some pieces of the course. It's not wide open for the public.
Did you go on Coursera?
Okay.
So Coursera has a version of Stanford's class which is just a bit less mathematical. Here, this is not a video, this is just the lecture notes of the class.
Okay, because I was looking there, there is a label for the class and
yeah, I mean,
there is some entries, but not the full classes. So
yeah, here's just the notes.
There is from methodology and
yeah.
How does SVM works for multi-class?
Yeah, I didn't talk about this, but I think it's enough, no? No, so for multi-class, okay, you have two main strategies, one versus all and one versus one. Let's talk just about one versus all. So one versus all, let's say you have three classes, dog, cat, bird. You are going to train three classifiers. The first one is dog or non-dog. The second one is cat or non-cat. And the third one is bird or non-bird. Okay? And then, so you are going to train three SVMs. You run the three. And then you are going to pick the SVM that is the most confident. What does it mean to be the most confident? So you have weight vector of cat times my X test plus B cat, okay, is equal to, let's say, 17. Same for dog, let's say, is equal to -5, and let's say for bird is equal to 0.8. Here I will say that I have a cat, because it's the most confident, it's the most positive number. Okay. So that's how you can generalize binary SVMs to multi-class SVMs. Any other question? No? Okay. Bon fin de semana.
Thanks for the best explanation of SVM. So much like, I don't know, half a dozen videos on the internet. And I think at the right level, intuition and math was really
Good.
I have a little present.
Oh, that's cool. What is this? I need to open. I still have to pack.